Okay, the first thing I'd like you to do tonight is get out this worksheet, Systems of Linear and Quadratic Equations. I want to take just a minute to go over it. If you didn't complete it fully, I'd like you to listen to what I explain and then continue that to be ready for tomorrow. You will potentially see one of these on your exam, so it's important that we focus on this. And just to reiterate, when you see a system of equations like this, a system means we have this bracket, which means we want to solve both equations at the same time. We want to find an x and a y value that's going to make the quadratic true and this linear function true. So by graphing, we know that the points that make it true that they share are their points of intersection. Okay. Now we also learned that by substitution, since these are both set equal to y, we could substitute this in place of this y, and in other words, we could set the two equations equal to each other. So x squared minus 3x plus 1 could be considered our left side, and 11/4 x minus 6 is our right side. They're set equal to each other. Algebraically, we could solve that. So there's two ways to really think about these problems. So in your homework, sometimes they gave you the system to solve and it was already set up with a bracket. And you would then go ahead and graph this. Now I'm just going to real quickly graph it by my own knowledge. This is a linear equation that hits the y-axis at 5 and it has a positive slope of rise 1, run 2. So it's maybe something that looks like this. The other equation I can see is a quadratic, hits the y-axis at 4, and it opens downward. Okay, so right now I'm potentially seeing that there's no solution. That's my initial idea before I've even graphed that. So I'm just going to verify that on the graph, but as you can see here, if we're looking for points of intersection, there are no points of intersection, so that would be no solution. But that needs to be verified on your calculator to make sure that I didn't make a mistake. Okay, if you look at something like number 5. Number 5, you're going to set this up. We want to solve this with a system, but it says to solve it algebraically. So algebraically means we're not going to graph it. We're going to use some algebraic concepts and we're going to use the substitution method. Since y equals this and y equals this, we're going to substitute x squared minus x minus 20 in place of this y. And we're going to get this expression. X squared minus x minus 20, that's our first y. And 3x plus 12 is our second y. And those are supposed to be equal to each other, so we set them equal. The next step is to set, we know that if we can make this one quadratic expression equal to 0, then we flash back to chapter 9 and we have all kinds of strategies for solving a quadratic set equal to 0. We can factor it, we can graph it, we can use quadratic formula. Okay, so when I subtract 3x, I get negative 4x. When I subtract 12 from both sides, I get negative 32. And to me, this jumps out to me as an easy factoring problem. Sorry, I wrote that wrong. So we need to find two numbers that multiply to get negative 32 and add to get negative 4. Well, immediately 8 and 4 jump out to me because 8 times 4 is 32 and the difference of 8 and 4 is 4. So I just need to work with the symbols. So if 8 is negative and 4 is positive, you multiply it, you get negative 32. When you add them, you get negative 4. So what that means is that I then factor it into this form. So you go to this step next. And now we solve. What value of x makes this 0? What value of x makes this 0? And that's how you would solve that. Okay, so if you haven't completed that correctly for 6, I'd like you to do 6 as well. And then 7, 8, and 9 are set up where it's already set equal to each other. So you really need to think about, we're trying to think about the equation y equals x squared and y equals negative 2x minus 1. So you can solve that by graphing or by setting them equal to 0. So this would become x squared. If I add 2x to both sides, if I add 1 to both sides, I need two numbers that multiply to get 1 and add to get 2. Well, that's pretty easy. That's going to be x plus 1 and x plus 1. So my solution is going to be when x is negative 1. Okay, so part of your work tonight is you need to finish this up. I'm going to give you a little bit of a lecture right now. You cannot check out. We have a lot of work still to do before the exam. You're going to be getting exam reviews, but we still have a whole nother chapter, and we've got about 7 instructional days. So you will be having videos every night trying to keep up, so make sure that you focus in. Okay, today's lesson is on special functions. And we've already looked at a few of them, but this first special function we haven't seen before. This is called a step function. So a step function, it says the graph of a step function is a series of disjointed line segments. Because each part of a step function is linear, this type of function is called a piecewise linear function. So that word piecewise just means that it's not continuous. It's in small little pieces. And if you jump down here and get an idea of what the step function looks like, it makes sense. It looks like a series of steps. And notice that each little segment ends up being linear. It's a horizontal line. One example of a step function is called the greatest integer function. And it's this new notation right here. Do not mistake that for absolute value symbols. That's the greatest integer function, where f of x is the greatest integer not greater than x. Okay, the greatest integer not greater than x. So let's see if we can make sense of this. So if we have this function, we want to do x plus 3, then we find the greatest integer of this. So using order of operations, we first have to evaluate the x plus 3 part. So let's just say that we pick x as negative 5. When you plug it in here, negative 5 plus 3 is negative 2. And we want the greatest integer not equal to negative 2, which is negative 2. Okay, let's continue. If x is negative 3.5, negative 3.5 plus 3 is negative 0.5. So we want the greatest integer that we can get greater than this, and so it's the next integer 1 lower. Yes. So we want the greatest integer not greater than this. So really we are bumping down to the next lowest integer. So it's going from negative 0.5 to negative 1. Okay, let's jump to this one and it will make a little more sense. When you put in negative 0.5 up here, we add 3, we get 2.5. We want the greatest integer not greater than this, so we round down to 2. Okay, so this greatest integer function is a little bit deceiving because when kids see greatest integer, they think that we're rounding up, but really what we're doing is we are rounding down. We are rounding down to the next integer. So this is often a shortcut or called the rounding down function. Okay, so when you graph this, let's just focus on this 2.5. When x is 2.5 right here, sorry, I lied. When x is negative 0.5 right here, negative 0.5. When we plug negative 0.5 into it, we got 2.5. Then we rounded it down to 2. If you notice, when you go up negative 2.5, it's hitting right there at 2. It's going to remain that until we get to 0. When x is 0, right here, when x is 0, 0 plus 3 is 3. The greatest integer less than or equal to 3 is 3. That's why right here at x equals 0, it bumps up to 3. So we have an open circle, the end of this limit, and it picks it up right there. Okay. Because the dots and circles overlap, the domain is all real numbers. So, as an example here, when x is 0, it is not included at 2, but it starts picking up right here at 3. So there's no place where an x value is not defined. Okay, let's try one. So we want to get an idea of what's happening here. So let's pick some values. Let's start with when x is 0. I need a better writing utensil. So when x is 0, 0 plus 1 is 1. The greatest integer less than or equal to 1 is 1. So we're going to go to 0, 1. Put a dot. When we go to 0.5, 0.5 plus 1 is 1.5. The greatest integer less than or equal to 1.5 is 1. So at a half, we're still going to be at 1. At 0.75, when you add 1 to it, you get 1.75. The greatest integer less than or equal to 1.75 is 1. So as you can see, this is all going to be a solid line. Ooh, little glitch in my... It's all going to be a solid line until we hit 1. As soon as we get, when x is 1, 1 plus 1 is 2. The greatest integer less than or equal to 2 is 2. So that's where we're going to put an open circle right here, and we're going to jump up and plot the point 1, comma 2. Then it's going to stay at 2 all the way until you get right here. When x is 2, 2 plus 1 is 3. The greatest integer less than or equal to 3 is 3, so it's going to jump up with a solid circle there. So can you see how the steps start with a solid circle, they continue, and then the end point's an open circle. Once you get this pattern, you can just continue it. So it's going to continue on, and you could check more points down here, but it's going to continue in both directions, stepping like that. Okay? All right. Let's jump. Well, we can try. Let's skip this one. This one you guys can do on your own. Okay, so make sure that you're trying all kinds of values to get an idea of where it's going. So when x is -1, -1 minus 1 is -2. The greatest integer less than or equal to -2 is -2. Okay, so now we have to see what it's going to do here. So -0.5 minus 1 is -1.5. But the greatest integer less than or equal to -1.5 is -2. So it's going to continue like this, and an open circle there. Because when x is 0, 0 minus 1 is negative 1. The greatest integer less than or equal to negative 1 is negative 1. So it's going to hit at 0, negative 1. When we get here to positive 1, 1 minus 1 is 0. The greatest integer less than or equal to 0 is 0. So you can see that the steps begin to jump like that. Okay. All right, turn the page. And this next one we've already done. This is the Vinny function. Absolute value functions is another piecewise linear function. Recall that the absolute value of a number is always non-negative. So in the absolute value function, written f of x equals the absolute value of x, all of the values of the range have to become positive. The absolute value function is called a piecewise defined function because it can be written using two or more expressions. Okay, so let's take a look at this. So we have f of x equals the absolute value of x plus 2. So when we start plotting these points here, when you do negative 5 plus 2 is negative 3. The absolute value of negative 3 is positive 3. Negative 4 plus 2 is negative 2. Absolute value of negative 2 is positive 2. And we begin to piece this together. Now, the reason this is considered defined is because if you were to cover just this portion up, couldn't you write a linear equation for this? Doesn't this hit the y-intercept at 2? And it has a slope of 1. So isn't that part x plus 2? So we would say this part is y equals x plus 2 when x is greater than or equal to negative 2. Because from right here, when x is negative 2 onward, this is the function. Now let's look at this other part. This part, if we were to extend this down, do you see that this piece would be defined as y equals, it hits the y-axis at negative 2, and it slopes downward at a rate of down 1 over 1, so it's negative x minus 2. But it's only this part when the x values are less than or equal to negative 2. It's okay that this one is greater than or equal to and this one's less than or equal to, because when it's exactly negative 2, both of those equations would work. Okay? So what you guys are going to do is I want you to make a small table for each of these and graph your absolute value functions. You don't have to go to this step yet. You're just going to graph the absolute value function. I explain that step because it kind of leads into our last type of piecewise function. Sometimes a piecewise function will give you both equations and the parameters. And trust me when I say it looks more difficult than it is. This is saying our function is x plus 1 if x is greater than 1. Well, what do you know about y equals x plus 1? Well, you should know that it's linear. It has a slope of 1 and a y-intercept of 1. So if we go down here and we do a y-intercept of 1 and a slope of 1, do you see that we're getting this line right here? But we only want this line when x values are greater than 1. So on our graph, here's x equals 0, here's x equals 1. As soon as we get greater than 1, we want to define that function. So we put a big circle here and we erase everything to the left of it because we only want this function for this part. After that, when x is less than or equal to 1, the function is y equals 3x. Well, y equals 3x has a y-intercept of 0, and it has a slope of 3. So that's graphed right here, but that's only for values of x that are less than or equal to 1. Since it says equal to 1, we want to put a solid dot on this graph, because a function can only be defined for one, every x value, so the x value of 1 can only have one dot on it. Otherwise, it's going to break the vertical line test for functions. So it's an open circle here, closed circle here, and this is called a piecewise linear function. Okay, so let's try this one. We're first going to graph this, negative x plus 4. So we go up here, 1, 2, 3, 4. Negative x means sloping downward. And the limit is if x is less than or equal to 1. So I want to go to x equals 1, and I want everything to the left. So I'm going to erase off all of this, and we want it equal to 1, and it's going forever in that direction. The other one is x minus 2, so this hits the y-intercept at negative 2, has a slope of 1. So we're looking at this graph. But this graph is the solution only when x is greater than 1. So down here, right when x is 1, we just want as soon as we get greater than 1, so we put an open circle, and it's everything to the right. So it's really important that you see at x equals 1, it's included in this top graph and it's excluded in this bottom graph. Why can it not be included in both? Because then it would not be a function. It would not pass the vertical line test. Okay, turn this over. This is what I'd like you to work on. I would like you to try 1 and 2, 4, 5 and 6, and then 7, 8, 9, and 10. So basically all we're cutting off is 3. Okay, I know it's spring. I know you've got a lot on your plate, but you have got to dig in and spend some time on this. We will not have time to spend an entire lesson tomorrow, another day on this. We're going to continue doing some practice, doing some work, but going into the next section. Have a good night.